Looks like we can get started. Welcome back, everyone. We're now on week 3 of the semester. And as usual, whenever we log into Canvas, I'll just have all the announcements sort of doodled here as you see. The big announcement for the day is that we have our exam 1 upcoming. This one's going to be on week 5. It'll be held on Monday. That means we won't actually have a lecture on Monday. And if the testing center that you selected is open late enough, you're welcome to schedule your exam right at the exam time, right at 6 o'clock. What I'll be doing before we even get into week 5, so on the very start of week number 4, I'll be directly sending a message to every single one of you individually in Canvas with instructions for scheduling your exam at your preferred testing center. So if you have not yet replied to the email or sent me a message of where you prefer to test at, for example, the Pocatello Testing Center or the Idaho Falls Testing Center, Twin Falls, Meridian, and so on, please do that as soon as you can, and I'll make sure to get you marked on the correct campus. Well, that's the major roundup of the announcements so far. Any questions at the moment about the exam or otherwise? Okay, we'll talk more about the exam in detail as we get closer and closer to that exam week. But another thing that'll be happening on the Canvas page, if you want to start studying early, taking a preview of the exam material, is after we go on to the weekend, again, before we even get into week number 4, I'll be working on filling out information here. I'll detail exactly which units are going to appear on exam 1. I mentioned a couple times throughout the course that I'm going to include some information on the very back. So I'll say what notes are attached as the last page on exam 1. And that will guide you for what you would like to include on your 1 page of notes. So I'll mention you are allowed to have a page of notes about this size, 8.5 by 11 inches, ordinary letter size, front and back with anything you like on it. You're welcome to have a scientific calculator as well, but I'll make all that stuff precise and detailed here as we get closer and closer to the exam date. I'll also be posting review questions down below right under the exam 1 so that you can practice typical problems that can show up on the first exam. But aside from that, we're just getting closer and closer to the exam date, so that's what's going to happen before we get into week 4. And at the start on Monday, I'll be contacting you. But otherwise, the other big thing going on is we assigned our very first quiz officially on Thursday's class. So this one will be due on this upcoming Thursday, the 29th. And I'll be posting before we get to our Thursday's class, probably on Wednesday, our quiz number 2 to be due the following week, just maintaining that pattern. I think that's pretty much it for me on my end of the announcements. Any questions or comments at all, folks, to start us out today? Okay, well, we're nearly done with the Unit 2B, and we're behind on the schedule a little bit already. I'm reading the textbook for the very first time and writing out these lecture notes for the very first time. And I think I made Units 2A, 2B quite long in the lecture notes. But, I feel like erroring on the side of a little more problems than too few problems is probably good for a course like this. But I'll try to keep it more contained in the upcoming sections. So we left off on example 7. That one had like 4 different parts, and we're on the final part of example 7. Here's what it looked like on that final part. We're looking into the size of different kinds of units. For example, we had interesting information talking about length, that a terameter, well, interesting question. We were asked a terameter is how many times as large as a micrometer. And the way we found that out is we went to this table from the textbook. What table is that? I don't think I actually wrote down the table number, but in the textbook for Unit 2B, there's this nice table here that gathers together all in one place this type of information. We compared the terameter, this part right here, by taking the ratio of 1 terameter divided by a micrometer. Using these units here, we put in 10 power 12 for the terameter. That's this part of the table. 10 to the power of negative 6 for the micrometer, and that was this part of the table, the 10 power negative 6. Once we threw that together, the units canceled off, and it was really just sorting out the exponential notation working with powers of 10. And we finally found that a terameter is 10 to the power of 18 times as large as a micrometer. That's a humongous number. And to do practice that one more time for our warm-up problem today, we'll do the same with gigawatt compared to a megawatt. First, any questions at all with the refresher question here, part C? Okay, well, first thing we probably want to do is cite that table we were looking at once again. So here it is. And the information we're comparing is gigawatt versus megawatt. So the prefixes are both giga and mega. Looks like we just need this part of the table to put down.
Oh, I like that.
There we go. So we just need that part of the table to put down. Let's put in the notes just to see how to work the problem. And the problem is about wattage, so we can throw in that unit as well as we get started. So for a megawatt, we would use the uppercase M, much like a megabyte, and maybe just W to stand for watts. So MW will stand for the megawatt. Likewise, GW will stand for a gigawatt. And this is the power of 10, so a megawatt is 10 to the power of 6 watts. And a gigawatt is 10 to the power of 9 watts. So the larger quantity we're comparing against is giga. So we'll be using that unit for the numerator against mega for watts. So this power of 10 in the denominator. So after all of that organization, we can get started and write down the computation. Starts with 1 gigawatt divided by now 1 megawatt. So 1 GW divided by 1 MW for megawatt. Now the next thing we do is we put in the power of 10. In the denominator, we have 10 to the power of 9 watts. Or just lowercase w for watts if you prefer. In the denominator, we have 10 to the power of 6 watts. And nice feature of this problem is units cancel, so we're just taking 10 power 9 divided by 10 power 6. Not sure why I was writing a fraction. Let me write it this way. Anyone happen to see what would happen with the exponential notation? What exponent would we get when we take 10 power 9 divided by 10 power 6?
Ten to the power of 4.
Close. It wouldn't be right on 4, but you're very close.
10 to the power of 3.
Yeah, exactly. This one would come out as power 3. So we can say 10 to the power 3 times as large. And just a refresher on the exponential notation, this is really two concepts just glued together, really. For this part right here, 10 power 6 divided by 10 power 9, we're using this idea. A base A, 10 or otherwise, to a power m divided by base A to a power n can be re-expressed as a base A to the power of m minus n. So we can take 9 minus 6 to come up with power 3. But a completely fine way to think about this also is you could rewrite 10 power 9 divided by 10 power 6 in this funny way. 10 power 9 is the same as 10 power 6 times 10 power 3. When you multiply these together, the exponents add up. And the reason I went with 10 power 6 is we already had a 10 power 6 in the denominator. And so now we can cancel that way and get 10 power 3. So either way we view it, either with the exponent law or by factoring, and which is again another different exponent law, that's where we would end up. Well, that finalizes the example 7 on this one, just comparing size of different kinds of units. Any last questions before we move on to the last question of these notes? Okay, last problem is all about density. And it's a kind of interesting question to start out. It says, the city-state of Monaco has a population of approximately 39,000 people living in an area of 2.02 square kilometers. We want to know the density of Monaco in terms of people per square kilometer. And sorry about the red there. Again, I forgot to include information about rounding and make it similar to the way this question is asked in my lab. So that's what the red is all about there. To even get started on this question, it's probably a good idea to define density in the first place. So here's our quick definition. We can say density, to stand for the population density, is going to be people divided by area. And the formula might seem kind of familiar in a certain sense because we had a different formula, distance equals rate divided by time, that we were using, say, earlier on around example 3 or 4, if I recall correctly. So it's a similar kind of formula, but just different kinds of quantities and units that we're using in this case. So to give this one a try, citing the formula that we see above, we'll write out the density of Monaco, or just density for short, will be the number of people. We have approximately 39,000 people. Divide by the area. We have an area of 2.02 in square kilometers. So we'll write in 2.02 km squared. And it's kind of a nice problem because now all we have to do at this stage is just divide. So here's the calculator portion of the problem. Take 39,000, divide by 2.02. It says round to the nearest integer, or nearest whole person, you could say differently. So if we rounded to the nearest integer value, the 9 there would round this up to 19,307 people. So we have 19,307 people per square kilometer, or km squared. So that's the density of Monaco. I would have never known that if not for reading this book. But now we can make an interesting comparison. We want to compare that in part B against the population density of the United States of America. But any questions or comments first on doing that computation there? Okay, really this question is kind of similar to the ones we were just looking into. We were asking and answering questions. How many times larger is a gigawatt versus a megawatt was our last question. And this one's not too different, just a new context, really. We're being asked, how many times greater is the population density of Monaco compared to USA, which has approximately 35 square people, or excuse me, 35 people, not square people. I don't know what that unit would mean. 35 people per square kilometer. So that's our approximate population density of USA. I believe this book was published around 2020, so you can think of all the data you get out of here being about 4 years old. But one thing that's kind of interesting about USA is it has vast rural area with hardly anyone around. And so we tend to be on the spectacularly low end for population density. And now we're comparing it to a country which looks pretty dense, to 39,000 or per 2.02 kilometers, or for the unit kilometer, we have this value. So if we compare the two values, we'll take the prior value computed, 19,307 people per square kilometer, divide by the figure we have for USA, just 35 people per square kilometer. Just like in the last problem, comparing, say, gigawatts to megawatts, the unit totally cancels, but it should. We're just getting a number of how many times greater. So all those units cancel, and the unit analysis is now over right at that stage. We're going to once again round to the nearest integer, and so here's what we'll get. Back into the calculator, this time it's 19,307 divided by 35. And so This one, once again, also rounds up to 552. So this will be 552 times as dense. So Monaco is 552 times more dense in terms of people per square kilometer than USA. And these figures would change if we, say, went to the city, New York, for example, or change it out to maybe to something more rural, maybe Rigby or something along those lines. But for the USA as a whole, this is the figure we would come up with the provided data. And just to highlight where the 35 went, we plug that into the denominator, the value for USA. Well, that was the last computation of the notes. Any last questions, folks, with the final topic, population density? Okay, well, the homework set for this section, 2B, is now going to be February 2nd. I'll make sure to double check the due dates in my lab. And so the pattern we'll be doing for the notes is the moment we finish a unit, the due date will be officially 1 week away. So that'll be the February 2nd on that one. Unit 2A, we finished last class, it looks like. So that one is due on we finished Wednesday, it looks like. That one is due on the 28th of this week. Well, we're now moving into Unit 2C. This will be the final unit that we cover in Chapter 2. It says, just very vaguely for the topic this time, problem-solving hints. And I'm reading the book for the very first time along with you, and I have to say, when I read this unit, 2C, I felt like the problems were really pretty challenging in this unit, almost as if the author was showing off a little bit with his favorite kind of tricky examples. So if you feel a little discouraged when you're reading through those examples, please don't. We're not going to try to throw in the homework, and definitely not on exams, any of those particularly very, very tricky problems that you might have seen in the reading. I try to keep this unit pretty short in the homework. I believe I just asked for 4 different problems that you'll be solving. And because it is a pretty tricky unit, I try to make the problems in the lecture notes very similar. So you can use the lecture notes as a pretty much problem by problem guide to help you get through if any questions come up. First, let me make sure to close this. And let's open up that next unit. So here's Unit 2C finally. Again, it's kind of a vague unit. It's not easy to tell what the topic is going to be all about until you read through the whole thing in full, do some of the problems. The author starts off with a discussion of different problem-solving hints 1 through 8, and does give more information, but I felt like it wouldn't be a bad idea to bring just some of these hints into the lecture notes, and we might refer back to these here and there as we're going through the problems. And again, these are some pretty random looking questions. This one is about the number of different types of tickets sold. Example 2 has something to do about a ribbon being wrapped around a mailing tube. Then we're getting into examples about length. And finally, something that's more familiar, or this is another area problem, and then something about pulling socks out of a drawer. So this will be kind of a random question. I guess there's 5 examples altogether, I miscounted. So we'll go through these, each one in turn, and think about the problem-solving hints as we get through each one of them. If we need, we'll pull up the units and work through this table as well whenever this information comes up. Well, hints 1 through 8, we're going to look on example 1, majorly hint number 1. There may be more than one answer. Let's put it down above the problem as a way to say, this problem seems to be all about, example 1 seems to be all about hint number 1. There may be more than more method. Consider similar problems. Sorry, that was a tongue twister out of nowhere. Equivalent problems with similar solutions is at hint 5. Hint 6 talks about approximations can be useful. Hint 7 is kind of an interesting statement. Try alternative patterns of thought. So we'll see which problem that might come in. And this is more just general advice. Do not spin your wheels. I think the author had really good advice there, where if you feel like you're just trying and trying a problem, you're writing out pages of scratch work, but nothing just seems to work to fit the problem, his advice is just walk away from the problem, kind of give yourself a refresh, even if you come back a day later, a couple hours later, or maybe just take the problem to class. You can always, at the very start of class, leave the problem and the homework alone, but mention at the start the problem that came up, and I'll be happy to discuss that whenever we call for questions at the very beginning of class. Well, let's start this one off. This one seems to be all about hint number one, but if we notice other hints might come into play, we'll mention them as well. It says a movie theater charging for a local matinee collects $6 for children, $10 for adults. So kind of a cheap theater in 2026 prices. And now they tell us at the end of the first hour, the theater collected exactly $120. Find all possible combinations of children and adults that could have attended. And this is kind of a weird question as well. If you needed that information, you might just, maybe you're the manager of the theater, you just ask the people who worked the counter. But if for some reason they just don't know, we can solve for this. But there's no unique answer to this problem. To get one unique answer, we would have to have some information that we're missing. We would need to know how many tickets were sold in order to determine how many tickets were adult tickets and how many were children tickets. Well, let's start off this problem by maybe organizing in this way. We want to find all possible combinations of children and adults that could have attended. So we can say, through a table here, this is where our answer is going to be. Let's split it into two for the two quantities. On the first column, well, the information starts with children, then adults. So I'll just keep that parallel so I don't get kind of mixed up in my mind and flip the values. We can say number of children. In this column, number of adults. In this column, I start just trying out combinations. You might see one already. If no children attended, and it's $10 for every adult ticket, that would mean 12 adults altogether. So that's one value. But then we'll have to brainstorm all of the other values, and it could be a lot of work to make sure you didn't miss one single combination to get through the entire question. So that's what makes this one a little bit trickier. So let's organize this even further. For number of children, let's compare that against the cost for each child ticket. For number of adults, let's compare that against this cost as well, $10 for adults. Instead of writing down the full word, number of children, let's put down a variable. Let's call this C is the number of children. C for children, A is going to be the number of adults. And now we're trying to get to this dollar amount. Aside from the price of the tickets, the only other thing we know is they collected exactly $120. So we can see how these quantities make up that $120 so that we can start filling out the possibilities in kind of an organized, logical way. Let's start by saying, if C is the number of children and it's $6 per children, we could write out this. Take C times $6 per children. Let me write it out this way. Plus, likewise, if A is the number of adults and it's $10 per adult, we can take 10 times A, the number of adults, and this should equal $120. That might seem kind of vague at first, why this has to come out as $120. So if we want to look at this really carefully, make sure the equation is just right, this is where our prior skills in the last two units, unit analysis, really comes into play. Let's look at that 6C very closely. If it's $6 and no cents, and that's per child, so per the one child, and we multiply it against a variable C, where C is number of children, times C, children, then units do cancel out in a nice way. Children and children cancel, and we just get 6 times C. But it has units, dollars, and that's great because the right-hand side has to have units of just dollars as well. It tells us taking 6 times C is on the right track, whether we wrote out the units or not. This is the verification side, the unit analysis, that's the right way to write it down. And same idea for 10 times A. It's $10 per adult. The per adult puts 1 adult in the denominator, canceling with adults here from that unit. So same idea, this would just be in terms of dollars as well. So now we've got a way to check our values. And now we just have to start listing up the values and see how we can get to $120. Let's go kind of in an orderly way. If we start off with, say, 0 adults whatsoever, so there's a 0 right where that A is, and we're trying to get to $120, we can find pretty quickly what C has to be. That would have to be, if we go into the calculator, 120 divided by 6 for 20 children altogether. So that would be kind of weird. Maybe it's a kid movie and the adults are probably supervising nearby. That's kind of a strange situation. But if we have 0 adults, 20 children, we should come out to $100 altogether. Another way to think about this is we can take this information right here and just throw it into the calculator. Take 6 times the number of children we're putting here, 20, plus 10 times the number of adults we put in, 0, comes out to 120. And just to keep the color coding in line, here's the parts right here we'll adjust. Really just this number here for number of children. And we'll also, in an orderly way, adjust this number here for the number of adults above. So now let's change the scenario. We're going to assume next that the number of adults is non-zero. Find the next possible number of adults that could work out, going from lowest to smallest. So I'm going to shrink this column, grow this column, increase the number of adults, which means we'll probably be shrinking this column, the number of children. So this is the approach so far. And a lot of it seems to be more about organization so that we don't take too long exploring all possibilities and happen to miss just one and feel like we're just stuck on that question for quite some time. So let's put in 1 adult. We're now up to $130, but we have to balance to 120. So if there's 1 adult, we need to drop the number of children in the problem. 19 children doesn't work, we're still at 120, $4. 18 children doesn't work, we're at $118. All that tells us is there's no possibility whatsoever with 1 adult. So let's try out the next possible combination. Let's increase this to 2 adults. We're up to $128. That means there's too many children in attendance. We've dropped this down to 17, still too high, $122. Drop it down to 16 children, and now we're too low. There's no middle ground. We can't put a decimal number of children. They have to be whole integer values. So it tells us 2 adults is impossible. And now we move up just to the next value. So we're going in a very, very slow, methodical way, making sure we don't miss anything. So here's the next value, 3 adults. The dollar sum exceeds the 120 where we're comparing right here. So that means we have to drop the number of children down to 15, but that works. If there's a 15 children in attendance with just 3 adults supervising and assuming, then plug in those values into the calculators we did, and we get the $120. So let's record our next possible answer. 15 children, 3 adults. So let's bring it into the table. And that's the name of the game so far for this one. It is tedious for sure, but the more you stare at this, the more you might see some patterns going on with this one. Notice that when we went from 0 adults to 3 adults, all we really did was add 3 there. Then when we went from 20 children to 15 children, all we did was subtract 5 to get to the next value down below. So if you notice that observation, you might be spending a little bit less time on the calculator. Let's see if this pattern still continues. Essentially, we're hunting for patterns really at this point to speed through the problem. So if we put in a new row, hoping for the best, let's go to the next entry here, put in 6 adults, drop this down by 5 so that there's 10 children. Let's just say, for the sake of conveying the pattern, this is what we did. Add 3 on this column, took the 15 and then minus 5 to get the next entry down on the column for children. But we also have a calculator, so let's verify if this works. So starting with 10 children, so 10 going into that side of the equation, move over to this portion, put in 6 adults, so 6 coming into this side of the equation, and it does in fact balance to 120. So that's kind of nice. It tells us we can kind of get through this by just observing the pattern from 2 rows, and that's all it would take. Any questions or comments at the moment? Okay, let's keep on putting entries and checking if they really work, just to be sure. This equation is kind of nice. This would be considered a linear equation, and that's why things seem to be kind of orderly as we go from one row down to the next. So on the next row, my guess would be 5 children. And here we're increasing, so let's put in 9 adults. So plus 3 here, continue with the minus 5 to get that 5 there. So the next values are 5 for the number of children, and my box is now off. I did not expect that. Let me fix this. So 5 here for the number of children, and now change the number of adults. That one's increasing to a value of 9. Bounces to 120. We're just always trying to hit that target. So that's the next possibility. And last would just be 0 and 12. So with 0 children and 12 adults, we added 3 here, subtracted 5 here, maintaining the pattern. That does seem sensible if you put in 0 children and you have 12 adults at a ticket cost of $10 per adult. We expect $120, but let me fix the calculator. That should be a 0 altogether. And there it is, the $120 we were expecting. So essentially, this is the whole answer right here. When it says find all possible combinations, this is what you would be adding into MyLab, these values here. Again, it's one of those questions where you can imagine this could take a while to think about, to get through, but with the assistance of a calculator, looking for patterns that we see in the output, it's a lot faster than expected. Well, any questions whatsoever, folks, in getting all these combinations? Okay, I would say this kind of fits in with hint 7. Try alternative patterns of thought, depending on your interpretation of what that might mean. I would consider that to be, in this context, look for patterns. We're all pretty great at pattern recognition. Sometimes that's what it means to be human. So leverage that against a problem. You can be surprised at how quick some of these questions could go. Other questions take a little bit more, so we'll revisit these hints as we go. In fact, just so that we can reference them easily, let me open a new file quickly here. What I hate to do is scroll all the way to the top every single time you want to refer to these. That can be kind of vertigo-inducing sometimes. So we'll refer to these as they come up on the next questions. All right, let's try out the example 2 next to change gears a little bit. I think example 2 is challenging for a number of reasons. One of the reasons is when I first read this question, the word mailing tube comes up, and wasn't really sure immediately what the mental image was in the back of my mind when they were referring to just an ordinary mailing tube. So to start this one out, let's get a good feel for what's going on by just looking up this word. Well, maybe reading the whole problem is probably the very first thing we should do. Example 2 says, suppose that a decorative ribbon is wrapped around a mailing tube 5 times. We're also told the tube is 24 inches long, has a circumference of 7 inches altogether. The ribbon goes from the very bottom of the tube to the very top, again, wound around 5 different times. And we need to know, how long is the ribbon? And this might be a really important problem. We work for some maybe big corporation and they're just happen to use mailing tubes. Maybe this is for maybe a Christmas announcement or Christmas party, and they want to construct, let's imagine, like 50 mailing tubes. They just need to know how much material do you need. So if you can find the amount of material, the length of the ribbon for just one mailing tube, we'd be on our way. Again, it all kind of boils down to what do we mean by this? So let's Google that one. Let's put here just generically mailing tube. Go to Google Images, and this is always a good idea just to get an idea what's going on. And here's our mailing tube, something you can send over US mail without getting something damaged. Say, for example, like a map or something along those lines. These could be architectural type plans that were drawn up. And this is our image now for a mailing tube. Let's draw one with the best of my artistic ability. It's not going to be the best drawing. Well, if we can put a drawing down on paper, it's going to assist us a lot in maneuvering through the problem, seeing what the question is really all about. Because it seems complicated with tubes being involved, cylinders, some kind of geometry problem where we're finding a length fundamentally. So let's start off this way. Here's that mailing tube. We're told it's going to be 24 inches long. So going this way, I'll think of this as 24 inches. It's not going to be perfectly drawn to scale, so we'll use our imagination as needed. We're also told it has a circumference of 7 inches. Well, that's just going to be the distance around. So from here, around here, that's the circumference. This, if we overlay with blue, is the circumference. So if we go from one end of the tube all the way around, we're told the circumference, we'll write as C, is 7 inches. Okay, so that's the mailing tube part and the dimensions. The problem gets interesting when we start talking about a ribbon. Okay, let's go to this part. If a ribbon goes from the very bottom to the top, it has to be wrapped around 5 different times. How long is the ribbon is the fundamental question. Let's insert this into the problem so far. Okay, so it says it goes from the very bottom of the tube. Mine's not standing up, so I'll just think of this as being the bottom of the tube. Here's where the ribbon starts. It goes to the very top, so I'll think of this as the top of the tube right up here. It's wrapped around 5 different times, so I won't be able to do this completely artistically, but I'll think of it wrapping around 1, 2, 3, 4, 5. Imagine these are completely exact distances apart from one another. And this is the ribbon being wrapped around. So it starts over here, it's coming around the back, and then we eventually see it come around like this, connecting around, and ends like that. Echo says, when we multiply the amount of times we get it wrapped around by the circumference, let's see. I think that's close, but it looks like it won't exactly be the circumference because it's being wrapped around as one full string where we never break it once. It comes around like this, all the way around, over and over again like that. So it won't be wrapped like this, a cut, then another wrap like this, a cut, and so on. The interpretation of this problem is wrapped around as one continuous string. where it's coming in at this weird little angle. So it starts here and ends there. Again, it's kind of a hard problem to visualize, but if we think of it in terms of, that's probably going to be kind of hard for me to draw. If we think in terms of it as a tube standing upwards in 3 dimensions, the string's kind of going like this, almost like a corkscrew, until it gets to the very, very top. Does that make sense with that so far? Okay, I think that's a great thought. And pretty much that's what's going on in these kinds of questions. What exactly are we really calculating is part of the problem itself. So for that interpretation, if they were just wrapping one little unit, making a cut, then doing another unit wrap around there, so just going around the circumference, then that would be absolutely what we would have done. Take 5 times their circumference, and then we would be done with this problem. But this one is a little bit more trickier in a certain sense. And with the drawing we have, we try to draw it as verbatim from what the information gave us, but we need a new view to really see what's going on in this problem. Caitlin says, would it be the length times the circumference divided by 5? I think that's pretty close too, but not quite on this one. I think it's going to come out as a slightly different value. It's a little harder to say why though. So the length of 24 inches times the circumference of 5 inches. Yeah, I like that thought. We're thinking about the dimensions of it, the way it's going to come together. I think it's going to be slightly different than that. And my challenge is to explain why exactly that must be. Other questions or thoughts so far? Thinking about the hints on this one, it's definitely not hint 1 any longer. I think I only had one example to really go along with this one. So let's strike this one through. That's harder than I thought. I thought that was easy to do. Where does strike through go on this? Well, let's not strike that one through, but let's just ignore it for the moment. Maybe more than one method. That might be true on this one. That one's hard for me to determine. I like hint 4, considers simpler, similar problems, but we have to use up the same information. But maybe one way to interpret hint number 4 in this problem is change the geometry so that it is easier to visualize. So in using hint 4, but think of it in this context, I think this is a good way to think about this one. Remember, we're looking at a mailing tube, something that we can actually make a cut on. Imagine you have some really nice scissors, maybe EMT shears, and you just cut that cardboard tube across here, and then you flattened it out. Now it's a rectangle, and it's going to be a lot more easy to visualize what's happening if all we're looking at is a rectangle versus the 3-dimensional tube, which is really, for me at least, hard to visualize geometrically. So here's the next approach, considering that hint. I'll say here, make a cut. Let's be specific. Make a horizontal cut. So say I'm cutting along the very, very top as it's sitting on a counter, and flatten. So now we're just going to press it down. It's going to turn into a rectangle. Any kind of tube or cylinder object like this, you could always take that action. And if we did that, here's what it would look like. Their circumference is going to turn into a width. So from this dimension of 7 inches, once we flatten it out, it's going to look like this. Let me try to keep it proportionate so it looks a little bit more believable. So width equals 7 inches going this way. We did have a length already of 24 inches going here to here. I'll copy that in black as it's written on the notes. So that dimension's the same, 24 inches. Going this way, this time for a length. This would be the bottom of the tube after flattened out. This other end, this was where the circumference was. It's now just a width as well after flattened. And now, if we made that cut, we also cut our ribbon a whole bunch of times, right? So we kind of ruined this. But just for the sake of visualization, let's say we glued the ribbon in place so it never moves. This dot right here connects with this dot from the very bottom, and it moves up in that kind of way. For the next spot here, let's go 2, 3, 4, 5 times wrapped around. Again, use your imagination that these are exactly equal widths apart. This next piece, after flattened, goes from here to here. Next piece, this one, goes from here to here. And again, we ruined this one, but at least we can compute something that's much easier to visualize. From here to here is this piece, and from the last one, we went from here to here, finally to what was the top. Okay, so now we have 7 different strips, and we want the total length of, 5 different strips, and we want the total length. That means if you can find the length of just one, all you are going to have to do is multiply it by 5. This problem is kind of a journey, though. Does that make sense so far with what we've drawn on paper? Okay. Well, the next thing we want to do is we took something complicated, we flattened it. That's a form of abstraction. We made the problem simpler in a certain sense, hint number 4. Now, this is still pretty busy information, but right where that red dot is, that's just a right triangle. So we can take this part right here. That looks too busy. Let me just use an arrow from inside that right triangle. And let's now laser focus on this object. I'm going to assume I'm zooming in on it a little bit. And that right triangle would look like this. Using the same colors for the ribbon and where we had a circumference. Oh, awesome. So now let's put in the 7 inches going this way. The unknown is this green line right here. So we could call it, say, let's go with lowercase c. And for this value, anyone see what we could do to get the length of this one black line segment by the question mark?
Can you divide the length by 1, 2, 3, by 5?
Yeah, good call. This, where the question mark is, came from right here. And we're always assuming that these are equal distances apart. So just like you said, we'll go the total length of 24 inches, divide by the number of different intervals we have, or regions, and that will give us 4.8 inches. So right where that question mark is, let's go 24, divide by 5, gives us the 4.8 inches going this way. So now we have a perfectly nice right triangle altogether. And whenever you have a right triangle, here's our massive tool that you might be thinking about already. Out of nowhere, we have Pythagorean's theorem. If I read this problem and I had to solve it on my own, and I never read the book to see how the author solved a pretty similar problem, I don't think I would have came up with this method or Pythagorean's theorem. Again, these problems are pretty tricky. So when you see them in the homework exercises, we're doing pretty similar ones as well in the lecture notes. So you can copy the process, see how it comes together. Pythagorean's theorem tells us that a squared plus b squared is going to be equal to c squared. Following the color coding that we see in this diagram right here, A is going to be the 7 inches, B is going to be the 4.8 inches, and C, well, that's the length of the hypotenuse. The trickiest thing about Pythagorean's theorem is you have to make sure the hypotenuse length is always on the far right side being squared. That's not too hard to identify in the right triangle. It's always the very longest side. Another way to think about it is we often write this little rectangle here to say 90 degrees, right triangle, and the longest segment, the hypotenuse, is always on the opposite end of the 90-degree segment that we draw in. So now we can start plugging in information. We can put in 7 squared. So that's the a squared part using the 7 inches plus 4.8 squared. So that's the other leg squared in the Pythagorean's theorem equals our unknown, which is c squared in this problem. Now we can throw this into the calculator. Move that down. So 7 squared plus 4.8 power 2 comes out as a 72.04. So 72.04 is now, actually, let's keep that grade, no harm. 72.04 equals c squared. And to solve this equation for the variable c, all we have to do is take the square root of both sides. So on paper, it would look like this. Square root 72.04 equals just c now on the right-hand side. Back down over here, we'll go, in this calculator, you type in SQRT, then 72.04. If you have a calculator nearby, this would be a good time to just double check how to compute that as well. Your square root button is going to be on the far left. Rounded to two decimal places, we get 8.49 inches. It doesn't solve the problem entirely, because when we say 8.49 inches, we're just talking about that one strip from here to here, which came from here at the very, very start of the problem, before we cut the tube. But there's 5 strips. So the problem finally ends when we take this quantity, 8.49, and just multiply it by 5. Again, this is a kind of an adventure on this kind of problem. I would never give you a brand new problem like this as an exam question because these are really long thinking kind of problems. They're really stressful in exam situations. So real exam questions coming from this unit are going to be kind of short and sweet and more direct. But for the sake of thinking about problem solving strategies as a homework problem, it's a pretty good problem, I would say. Let's summarize what we know so far. The length of 1/5 of the ribbon is 8.49 inches. We're saying 1/5 of the ribbon because this is that piece of the ribbon wrapped around 5 times, but we only found one total length. So that means to get the, or one length, not the total length. So to get the total length of this ribbon, all we have to do is say total length is 5 times 8.49 inches. So this will be our final computation to get the end figure on this one. 5 times 8.49, coming out to 42.45 inches altogether. So again, this one is a pretty bizarro kind of problem in a certain sense. It's really stretching our imagination, seeing things in 3 dimensions, flattening it to 2 dimensions, and then just looking at one small piece so we can analyze through Pythagorean's theorem to get the end result. Any last questions or comments getting through this problem in full? Okay, thanks for the suggestions and the thoughts on this one. Again, it's really hard to tell and sometimes really surprising how a problem is going to go. And this is just one way to do it. If I'm being completely honest, I read the book first before attempting a problem like this one, so I pretty much just copied the author's method when he solved his. If you see a different way to get at this problem, some unique, clever way, and you come up with this particular value, it's just as good. It's even better if it's a more direct solution because this one took some stages to work through. So let me know if you had some inspiration on a different way. coming up with the same value, I'd be happy to discuss it in class. But let's change gears then to the next problem on the table. Example 3. This is out of 5 examples, so again, this will be a kind of a shorter set of notes. We're not going to spend days doing the really, really hard problems like these. But this problem is actually pretty similar to the one we just did. Pythagorean's theorem comes into play in the most bizarre kind of way once again. Maybe not as strange as the last problem, but certainly kind of unexpected at first. It says to start, imagine a bridge that is exactly 1 kilometer long. So we have that to begin with. Since that's a pretty important quantity, let me start by putting that highlighting in. On a very hot summer day, the bridge expands by 10 centimeters. That might be a concern. Hopefully the engineers have accounted for this so we don't have any collapse on the bridge, any structural damage. But that's an interesting expansion. We have kind of different sort of units going together, so let's focus on these, maybe before we go through the whole problem. The rest of the problem says, if the bridge buckles and the center rises up in a triangle shape, triangle specifically, so that we can calculate something exactly, approximately how many meters high would the center be above its normal height? So we're imagining a 1 kilometer long bridge. Let's actually start drawing this. So we'll go from here to here. Probably will help if we write this in blue to capture the information above. So here to here is the 1 kilometer. 1 kilometer, if we see our guide on units from the last section, is just 10 to the power 3 meters. So we can use that information if we so choose, bring it all the units down to a similar unit and say 10 to the power 3 m for meters, or 1,000 m for meters altogether. So from one end of the bridge to the other, we have a total length of 1,000 meters. Okay, so that starts it off. Now again, it says, on a very hot summer day, the bridge expands by 10 centimeters. And compared to a kilometer, that doesn't seem like much. Let's do some unit analysis on that, choosing the unit of meter. So 10 centimeters will be 10 times 1 centimeter. That step isn't required, but I think it's a good way to just break down the problem. Because at 1 centimeter there, we can put in 10 to the power negative 2 meters. So let's put in that unit analysis here. So we have 10 times 10 to the power negative 2 meters. Let's look at that guide once again from unit 2b. So right where it said 1 centimeter, I put in the power 10 power negative 2, so that's this figure here. And the 10 is just, other 10 has just been copying down. So we have 10 times 10 power negative 2. You can think of that exponent as being 10 power 1, and this comes together as add across the exponents. 1 plus a negative 2 will give us 10 power negative 1 meters, or altogether 0.1 meters, or just m for meters if you prefer. So that's the new expansion. But it doesn't just expand completely horizontally. The new drama in the problem is it buckles. So it's going to rise up, and we're told it rises up in a weird way. I'm not sure if this would happen in reality. It'd probably be more like a semicircle. But we're imagining it buckles, and the center rises up into some triangular shape. So this might be kind of exaggerating, but I'm going to imagine the top of that triangle to be right here at its center, kind of hide, but just a way to capture the information from here when it says it buckles into a triangular shape. We'll go from here to here. So let me highlight that. This length is a new length. It's not the length of the whole bridge any longer, 1,000 meters. because remember it's expanded by 10 centimeters. This is the new shape, but that means we have a new length at the same time. So let's write in new length will be equal to the old length, which was 1,000 meters, plus the expansion amount. It grew by 0.01 meters. I said that weird. 0.1 meters, not 0.01, or just 0.1 meters is a better way to say that. So the new length of this bridge is going to be altogether 1,000.1 meters. And that will be the length from here to here, down to here. Well, we copied in all the information. The major question they're asking is here. How high would the center of the bridge be above its normal height, which is right where the red dot is? We were very concerned at what's happening in the center, it turns out. So we're going from here up to that height. That tick mark might be a little bit too over exaggerated, but let's put a little H here to stand for height. Okay, so that's a lot of information to put in together so far. We pretty much exhausted all the material they gave us. Now we have to try something. It's a pretty complicated looking diagram, but the tie into the last question is, we have a 90-degree measurement going this way. Both sides of the right triangle are identical, or the left side is a right triangle, the right side is a right triangle, and they are identical as triangles. So we can take this whole triangle, abstract away into this new diagram. We have a distance going this way. That's a little bit too exaggerated. Let me try to make it look proportionate. That's going to be the hypotenuse. We often write that as a C in Pythagorean's theorem. We have a length going here to here, ending at this spot. And what we want is this value here, the height. But there's some unknowns so far. We need a value A. We need a value C. If we can't get at least two values out of the three, A, C, and the height H, then we're stuck in this problem. This problem was asking us to solve for the height. So that tells us we probably don't have a value for that ready to go. But now we need two different values to even start with Pythagorean's theorem. Any volunteers to find one value or another?
Would A be 500 meters because it's half of the whole length?
Yeah, absolutely. Good call. The total length is 1,000 meters. We're cutting it directly in half, like you said. So here is 500 meters. So that gives us that value there. So A is going to be just half of that length going in here. And would you all agree the logic is the same for the value of C? If the entire length from here to here is 1,000.1 meters, we should just be able to divide it by 2. So let's give that a try. With the same logic from before, go 1,000.1 meters. Again, it's just a little bit more because of the thermal expansion. Divide by 2, and we have 500.05 meters for the hypotenuse. So going this way, 500.05 meters. Again, the height is kind of exaggerated just so that the diagram is a little bit readable. Things aren't compressed too much in the scale. So it's not perfectly to scale. This whole diagram is just to capture the information. Well, any questions at the moment, folks, putting that down? Okay, at this stage, we're into the Pythagorean theorem portion of the problem. And Pythagorean's theorem is sometimes a tricky one to write down just right. Major thing you want to focus on is the length of the hypotenuse. Like we mentioned, It's the length opposite of where you have a 90-degree square measurement right here. Or a great foolproof way to think about it is it's the longest line segment you see whatsoever on your right triangle. And when you write down Pythagorean's theorem, start by saying that longest length should be on the right-hand side, all on its own, squared. But the rest of the values, whether you call them A's, B's, or maybe you called it H because the height was what you were solving for, as long as they're on the left-hand side in any order you write them, you've got the right version of Pythagorean's theorem. So we'll go a squared plus h squared. That ties in on the value for what we're trying to solve for in the question. And now it's a matter of just plugging in these values. So a squared is going to be 500 squared going there. We're just making substitutions from what we see in the diagram. H, we don't know what that one is, so we'll just leave it as is, plus h squared equals C is 500.05, so we need to square that value. Now we can organize this a little bit easier to put in the calculator if we subtract that 500 squared. Write in next, h squared equals 500.05 squared minus that 500 squared. And now we're ready to drop this into the calculator. So take 500.05, raise it to power 2. The power 2 button is like an up arrow you see in your calculator. Up nearby, I think it's above the square root button. Minus 500 and square it. And we get 50.0025. Notice it says round the final value to 2 decimal places. So we need to keep in exactly what we see here and not round early on this problem, or we could actually make a pretty appreciable difference on the final answer. So 500.0025, 50.0025. Last step is just like before on the prior problem. We square root both sides, we're on our way. Let me scroll to the right place here. The height is a root of 50. I don't know why I want to say 500. 50.0025. That's a 0 there if you were wondering. And just about there, let's say square root 50.0025. Now we can round the final value to the 2 decimal places to get a 7.07. And this is not inches, this is meters. This is pretty tall altogether, which is surprising that a thermal expansion is so tiny of 10 centimeters. If it buckles in this kind of shape, that's quite high, 7.07 meters altogether. But that's where the question finally ends at that stage. We could say the bridge will be 7.07 meters above the normal height. And that would be specifically at the center. Well, again, these questions are pretty tough. A lot of these problems, I wouldn't expect Pythagorean theorem to even come up at all. This one had a bigger hint when they told us a triangle shape is going to come up. But we still had to write down something, put in the right values, and by being very careful, methodical step by step, we were able to determine 500 meters this way, 500.05 meters that way. And to me, right where the red dot is, those 2 values, that's the hardest part of the problem. If you can get those in just right, then Pythagorean's theorem is kind of just a plug stuff into a formula and solve process. But at the same time, we had to be very mindful of the units, do the unit analysis to get that 1,000 meters or 1,000.1 meters in the very first place. Well, when we come back on Wednesday's class, we'll be finishing off the next 2 examples on these notes and then moving on to the chapter 3 unit. But any last questions at all, folks, before we call it a night today? Okay, if you want to get started on Unit 2C, we did most of the questions that you'll see in the homework. There's just two other questions that we haven't quite gotten to yet. So you're welcome to start early and see how those go. But have a great night, folks. We'll be back into example 4 when we come back on Wednesday. Take care.